moment as we worked out getting the code to everyone and starting a few minutes late. I am Karen Fox with NASA's Office of Communication at NASA headquarters, and we are here today to talk about Europa Clipper, which had a key milestone today. And we have ready to talk Nicola Fox, the Associate Administrator for Science at NASA headquarters, Laurie Leshin, the Director of JPL, Curt Niebur, who is our program scientist for Europa Clipper here at NASA headquarters, and Jordan Evans, the Europa Clipper project manager, also at JPL. With no further ado, I'm going to toss to them to speak, and then we will take questions afterwards. Nikki, please.
Thanks, everybody. Good afternoon, and it is wonderful to be here with incredibly good news. So we're all very happy here, extremely hot off the press. We did just put the Europa Clipper mission through the key milestone review here that we call KDPE, so the last sort of big review before we really get into that launch fever. And we're really happy to say that they unequivocally passed that review today. So it's just a really exciting time. As you all know, at NASA we strive to answer these really fundamental questions about our solar system and about our place in it. And Europa Clipper will bring us even closer to that answer. We always like to think about how science enables exploration and exploration enables science. And Europa Clipper is an incredibly important part of our Science Mission Directorate portfolio. Now, as you're going to hear from some of the other speakers, scientists believe that Jupiter's icy moon, Europa, has the suitable conditions below its surface to be able to support life, and those ingredients are water, energy, and chemistry. By studying this, by flying close to that moon and flying through kind of the plumes that come up, it will help us better understand the astrobiology and the potential for habitable worlds beyond our home planet. As we all know, sending a mission into space is hard. We always say that space is not for the faint of heart. And it's even more ambitious to send this largest spacecraft that NASA's ever built for planetary exploration, and it will travel into the incredibly harsh radiation environment around Jupiter. We're proud of our incredible teams here at NASA, at JPL, and of course with our incredible industry partners who together have worked tirelessly to overcome lots and lots of challenges to get this mission ready for the launch pad and to get it there on time. And even when presented with an incredibly stiff challenge very recently, the team just pulled out all of the stops. They really worked together, and they delivered a solution that will ensure that our mission to explore this ocean world will be able to sustain this incredibly harsh radiation environment around Jupiter. So I, for one, cannot wait for Europa Clipper's launch next month, and I'm even more excited to see all of the incredible and the unprecedented science that our science community has been waiting for decades. So I look forward to the incredible science that we will get for Clipper in the generations to come. As always, NASA science will continue to deliver every second of every day. And as I pass over to my dear friend Laurie Leshin, I will say to her, go Europa Clipper.
All right. Thank you, Nikki. Thank you for your incredible support, everyone here in SMD, and thank you to our Europa Clipper team for their extraordinary efforts, which were also lauded in today's NASA review. I am thrilled to say that we are confident that our beautiful spacecraft and capable team are ready for launch, operations, and our full science mission at Europa. As you all have probably heard, we have undertaken rigorous testing in recent months and analysis to be sure that our transistors on Europa Clipper will be able to withstand the harsh radiation environment at Jupiter and its moon Europa. This was a huge lift, and I think huge lift is a huge understatement. It was done with our usual high standards and exacting approach honed over JPL's decades of experience in developing, managing, and operating deep space missions. Getting to this milestone required shoulder-to-shoulder collaboration even beyond JPL. We worked, of course, with our colleagues at NASA headquarters. We had tests going not only in every facility we could find at JPL, but also every facility we could find at NASA Goddard and also at Johns Hopkins Applied Physics Laboratory. It was an incredible team effort, and we're so grateful for all the support. Right now, we're moving full speed ahead towards the opening of our launch window on October 10th, and soon the spacecraft will lift off from Kennedy Space Center, and then it's off to Jupiter. So go Team Clipper. We're excited and ready to carry out Europa Clipper's mission as planned. So we are on what we would call our baseline science plan, the plan that we had before we discovered the challenge with the transistors. We are now confident that we can deliver that mission, which will deliver incredible science. First, we have to make a 1.8 billion mile journey to get to Jupiter in 2030. And our spacecraft, as you heard from Nikki, is designed to explore and observe the icy ocean moon Europa exclusively and thoroughly. It'll make 49 science-gathering close flybys past Europa over the course of its 4-year science mission. It has a stunning array of sensors, 10 science investigations that will help us understand Europa's icy crust and global ocean that we suspect lies beneath it, as well as determine its chemical composition and geology. The mission's detailed exploration of Europa will help determine whether the moon could support life as we know it, whether its environment is habitable. At JPL, we're very proud to manage the Europa Clipper mission, the largest spacecraft NASA has ever built for a planetary mission and one of the largest ever to be assembled in our clean room. JPL is the world leader in planetary and deep space robotic exploration with decades of unique and deeply technical experience, and we needed every bit of it in getting this spacecraft ready for launch. Our missions have visited every planet in our solar system, and of course there's the Voyagers that are even beyond the solar system. At JPL, our motto is Dare Mighty Things Together, and Europa Clipper is a testament to how we do just that. About 4,000 people across the U.S. and Europe have worked on this mission since it was officially approved in 2015. Many of them will continue their work on it, and many thousands more will be involved in flying it and involved in the science for decades to come, because this data will change the textbooks, will give us generations of new knowledge about the incredible moon Europa. So I'm excited to say that we've met this moment and we can't wait to be on our way to Europa. Now I'm going to throw it over to Curt Niebur, Program Scientist for Europa Clipper.
Thanks, Laurie. Laurie just mentioned that the sheer number of people that have contributed to get us where we are today. So I'd like to touch very briefly on the amount of time that it's taken to get us to where we are today. When I started at NASA headquarters in 2003, I was given the challenge of pushing a Europa mission forward. And I began that thinking that I had a really solid appreciation of how long and difficult the road ahead was going to be. And I was completely and utterly wrong about that. It was much harder than I anticipated. And it felt like it simply got harder and harder with each year that went by. And there was no harder year than this past year, and especially this past summer. There was simply challenge after challenge after challenge, culminating in the MOSFET transistor problem that we've recently overcome. But through all of that, through all those years, the one thing that we never doubted was that this was going to be worth it. Because as Laurie said, this is an epic mission. It's a chance for us to explore not a world that might have been habitable billions of years ago, but a world that might be habitable today, right now. A chance to do the first exploration of this new kind of world that we've discovered very recently called an ocean world that is just totally immersed and covered in a liquid water ocean, completely unlike anything we've seen before. That's what's awaiting us at Europa. That's what Europa Clipper and her team are going to unveil for us. And it has definitely been worth the wait. It's been worth the hard work. And right now I want to hand it over to Jordan Evans, who's the project manager. And it's Jordan and his team that have gotten us here. At the beginning of the summer, I shared with Jordan that I was worried that we were asking the impossible of this team and that it was just too much. And Jordan and the team completely delivered on the impossible. They saved this mission this summer. They're the ones that have opened the way for us to get this spacecraft to the launch pad and then get the spacecraft to Europa so that the science can start. So, Jordan, I just want to say thank you very much.
Wow, thank you very much, Curt. And I'll start by saying we are ready for Jupiter. Now that we've completed this key NASA review, we're focused on heading towards the launch pad, doing the final preparations. Our launch period opens October 10th, and we're on track to start that journey to Jupiter. One big challenge was analyzing how those transistors on the spacecraft would handle the radiation environment at Jupiter. And after extensive testing and analysis of the transistors, the Europa Clipper project, and I personally have high confidence that we can complete the original mission for exploring Europa as planned. It's a very difficult environment in terms of radiation at Europa. Jupiter is engulfed in more radiation than any planet in our solar system. That's one of the reasons why exploring the Jupiter system is so challenging. The radiation near Jupiter is a kind of space weather. It bombards everything in its sphere of influence with damaging particles. The planet's giant magnetic field acts as a particle accelerator. It captures those particles, accelerates charged particles to create these powerful radiation belts. And Europa sits near the outer edge of the worst part of that radiation belt. And so flying near Europa exposes us to this high flux of damaging particles. And so the mission engineers on Europa Clipper need to be sure that the spacecraft components can survive that radiation environment for the duration of our 4-year prime mission. As soon as we had learned that there might be an issue with our transistors, which was back at the beginning of May at JPL, we moved quickly as a project and as a lab and agency with our partners as well to quickly analyze the risks and conduct tests. Generated a tremendous amount of data. We know a lot about the Jupiter radiation environment from previous NASA missions, including the current Juno mission, which is at Jupiter right now. We completed extensive testing to validate the transistors on the spacecraft. We ran tests 24 hours a day over the last 4 months at multiple locations, at the Jet Propulsion Laboratory, at the Applied Physics Laboratory, and at the NASA Goddard Space Flight Center. We simulated flight-like conditions to illuminate any issues that the transistors might have over our 4-year science mission across the variety of applications we have on the spacecraft. We put these representative transistors into these environments, irradiated entire circuits, and to see how the system behaves, and not just the transistors themselves. We looked at transistor temperatures while the spacecraft was outside of Jupiter's most intense radiation environment to determine how much recovery we might be able to get from these transistors while we're not in that intense radiation environment after each flyby. We've replicated that transistor self-healing, or annealing as it's called, that occurs by heating them to room temperature while they essentially rest far from that intense radiation environment as we go around each orbit of Jupiter before rendezvousing back with Europa again. The underlying issue was that there was a gap in the way in how industry qualifies the kind of hardware like MOSFETs for high radiation environments. The parts in question, the semiconductor in the transistors, are cut from silicon wafers, and those silicon wafers met the radiation hardness requirements that we needed. But then those semiconductor wafers degraded while in storage. We concluded after all of this testing that during our orbits around Jupiter, while Europa Clipper does dip into the radiation environment, once it comes out long enough for those transistors the opportunity to heal and partially recover between flybys. We're going to continue to closely monitor both the radiation environment, we have a radiation monitor on board, as well as the performance of the transistors from the ground once we are in flight and once we arrive at the Jupiter system. To accomplish this, we've received help from many corners, including the vendor. The vendor's been immensely proactive and helpful throughout all of our work. To reiterate what's already been said, we can, and I have very high confidence, and the data bears it out, complete the original mission, which is 49 flybys of Europa, and amounts to 80 orbits of Jupiter over that 4-year period. Our spacecraft itself is currently in ATLA, or Assembly, Test, and Launch Operations, at the Kennedy Space Center. A couple of weeks ago, we installed the immense solar arrays on the spacecraft, and now that we've completed this key NASA review, we are ready for our final launch preparations and reviews, and we are ready for Europa. At this point, I'll hand it back to you, Karen.
Woohoo!
Hey, yeah. Can you tolerate?
Fantastic. Thank you all. We do have some questions on the line. As a reminder, if you want to get into the queue to ask a question, go ahead and press *1. Our first question is from Jeff Faust with Space News.
Hey, good afternoon. Just to make sure I fully understand this, you've confirmed that the transistors can handle the radiation environment and you don't need to modify any aspects of, say, the trajectory the spacecraft is going to take during the Europa flybys, given your understanding of how they respond to the radiation environment. So, in other words, you can proceed with the mission as earlier planned. You're not making any changes to the mission as a result of these studies. Thanks.
Yeah, Jeff, that is correct. The mission trajectory is the exact same mission trajectory that we've been planning and studying for the past 2+ years as a science team.
And that was Jordan Evans who was speaking, and I'll remind speakers just to identify themselves before they answer questions. We'll try to remember to do that on our side. Thank you so much. Our next question is from Marcia Dunn with the Associated Press.
Yes, hi. You mentioned that there may be some degradation of these transistors during the high radiation periods, but they can heal when they come out of this intense zone. How much time elapses between these flybys with the intensive radiation, and how can you be so sure that they'll heal properly enough to be able to carry out the mission as planned? Thank you.
This is Jordan Evans again. For the first half of our mission, we fly on a 21-day orbit around Jupiter, and so one day of that 21 days is the flyby, and that's when we are in that intense radiation environment. So we have 20 days outside of that environment. All of the testing that we did when we looked at that healing, at that annealing, we used durations that were far smaller than that. So we were conservative in our testing to show that we understood how much annealing time we would need, and then demonstrate that we had far more than that with margin over each of the Jupiter orbits.
Fantastic. Thank you so much. Our next question is from Bill Harwood.
Yeah, hey, thank you very much, and I think this is for Jordan as well. I'm just wondering, can you take another crack at explaining exactly what the radiation does to the transistors? I'm not sure physically what's going on, and when you say it's annealing or healing or whatever it's doing, how does it get restored to its or close to its original state? That's number one. Number two is, how many of these transistors are on board the spacecraft in total? Thanks.
This is Jordan again. So it's device-level physics, right? These are metal oxide field effect transistors. So think of them as electronic switches where you apply a voltage and you can close an electronic switch. And so understanding how the behavior of that switch and the amount of voltage it takes to turn it on or off degrades over radiation is something that is well known in industry, as well as understanding then how getting out of that environment and warming it may restore some of that damage. That's the first question. The second question, these transistors exist all across the spacecraft. I can say that we have 200 unique applications where it may be duplicated multiple times, but in different circuits across all the spacecraft and the instruments.
Thank you so much. Moving on to our next question, which is with Joel Achenbach from the Washington Post.
Thank you very much. Are there other aspects of the mission where you have a critical path or a potential single-point failure, other than the transistors, that you are focused on, or that will get a lot of attention? In other words, other engineering challenges. And a second question, if I could, is: will this mission determine if there's life under the icy crust of Europa, or will it only determine that there might be life? In other words, could you detect living things with this mission?
Why don't you say this?
This is Curt Niebur. It's important to note that Europa Clipper is not a life detection mission, and there are two reasons for that. One is it would be premature. The first thing we need to do is figure out, are the proper ingredients there to support life as we know it? And as Dr. Fox mentioned, we're reasonably confident that almost all of those ingredients are there, but we don't know for sure. So we need to answer the habitability question first. And the reason we need to answer the habitability question first is because of the second reason. We don't have a life detector. There's no such thing as a tricorder instrument that we can point at something and it returns a blip or a blop telling us if it's alive or not. It is extremely difficult to be able to detect life, especially from orbit. So first we're going to ask the straightforward question. Are the proper ingredients there for life to exist? And you can bet your bottom dollar that if Europa Clipper tells us, yes, those ingredients are there, that we are going to be knocking on the door fighting for a second mission to go looking for life.
Can I just add one thing to that? This is Laurie. Hey, Joel. The thing we will learn with Europa Clipper is where follow-up missions might want to go, right? We'll learn where the ice might be thinned, where there could be upwelling of water from the ocean in modern times. And so we're going to learn a lot about how to get smarter about asking that question over time.
And this is Nikki, working in concert with the James Webb Space Telescope that just took the amazing images of Europa Clipper, showing us these incredible plumes is just even more tantalizing for how important it is for us to go and make these close flybys.
And then this is Jordan Evans responding to the question about the critical path. The critical path at this point goes through the spacecraft itself. So the next steps at the Kennedy Space Center are the final closeouts, install before flight items, the remove before flight items, fueling the vehicle, which starts later this week, and then ultimately the joint operations that we have with the launch vehicle, attaching to the payload fitting, encapsulating into the fairing, and then rolling out to the pad.
Jordan, and again, this is Laurie, they're not working any additional major technical issues at this time.
Excellent point. We, in this review today, we are green for technical.
Normal.
That is
normal work to go to get to launch.
Yeah. We are technical green.
Woohoo! Feels great to say that.
All right, thank you so much. Our next question is from Lisa Grossman with Science News. Lisa, are you there? All right, since we can't hear Lisa now, I'm going to move on to the next question, which is David Brown with the New York Times.
Hi, this question is for Dr. Fox and Dr. Niebur. It's my understanding that not long after the MOSFET issue was discovered and the extent of the problem was still uncertain, the project presented a suite of options to NASA headquarters. Among them was descoping the mission to a smaller number of flybys so that the launch window could still be made. How would you each characterize your response to that option?
Thanks for the question. It's exactly what I would expect any good mission team to do, which was they came and they presented, as you said, a suite of options. Obviously, the perfect outcome is the one that we've had, which is being able to figure out a way to keep the mission exactly at the full science that we wanted to have, but it was certainly an option. If you don't want to not fly a mission, and if there's a way to get some science, even if it's not as much as you might have originally wanted, it is still better to get some science. And so we really thanked the team for coming up with a different kind of a different flight path, if you like, for the mission. But we're very grateful that we did not have to go with that option, and we were able to take advantage of the incredible work from the team, and we are able to, as Laurie said in her remarks, achieve the full science of the mission. Curt?
I would just add that I was very gratified from the beginning all the way through to the end to see the level of commitment among everybody working this problem, not just to fix the problem, but to remain committed to the full science of the mission.
Thank you so much. Our next question is from Stephen Clark with Ars Technica.
Thank you. I think my question's probably for Jordan. You're talking about being able to collect the full science, baseline mission, no changes to the trajectory. Any changes at all in the way you operate the spacecraft to be able to meet that baseline mission with this transistor issue, or did all the testing simply show that the transistors will work for the baseline mission? And then any risk or concern going forward with a potential extended mission that this may put that in jeopardy? Thanks.
Very good. Yeah, this is Jordan responding. So regarding the first question, the changes, I talked about the healing, the annealing that happens outside of the radiation environment. That annealing is improved with temperature, and so two of our colder instruments that are outside of our fluid loop that warms the remaining components of the spacecraft, they operate at a colder temperature by design in order to minimize the energy. And so changing their software-controlled heater set points to a slightly warmer temperature is the impact. So instead of dialing the thermostat to one temperature, you dial it a little bit warmer when you're outside of the radiation environment, and that warms them up. In terms of the potential for an extended mission, I'll say that all of these 200 unique applications are were looked at, and then independently looked at by outside folks to look at circuit margins and ensure that with the MOSFETs that are present on the vehicle, that we would have appropriate voltage margin. And so that voltage margin is not necessarily for an extended mission. It's for things that happen in complex missions in uncertain environments. But those margins are there. They are positive. And they give us good confidence, certainly in the baseline mission, but not that we would expect it to just immediately drop off right after that.
Right, now I'll just add to that, Stephen, this is Nikki, just that we are looking forward to their extended mission. So as Jordan said, they have margin, and we have no reason to expect anything other than a great 4 years and an extended mission beyond that.
All right, thank you very much. We're going to do Lisa Grossman again from Science News. Let's hope it works this time. Sorry about that, Lisa. Your turn.
Hi, can you hear me now?
Yes.
Hi, I actually was going to ask about the extended mission as well, so thank you. That was my question.
So you're good? It's all right.
Another vote for an extended mission.
Thank you. All right. Our next person then will be Irene Klotz with Aviation News, please.
Thanks, Karen. I was wondering if the launch to be ready for an October 10th launch, do you need the 39A by September 14th, or is that able to slip a couple days?
So this is Nikki. That is all part of the negotiations that are handled for us by the Launch Services Program at Kennedy, NASA's Kennedy Space Center, and they are watching many launches. The wonderful thing about Kennedy right now is it is an incredibly active spaceport, and so they are watching and they are helping us to deconflict many launches that will be at the Cape at the same time.
Thank you so much. Our next question is from Isam Ahmed with AFP.
Hi, thanks again. Just to go back to the question about this is not being a detection mission, could you maybe just expand a little on what's your sort of best outcome scenarios in terms of what we can gather from Europa Clipper, and what are the worst outcomes? And sorry, very quick follow-up on the transistors. Are these sort of stock transistors, nothing special about them, or are they in any way sort of high-tech? A quick Google talked about nanowire transistors specifically built to withstand cosmic rays. Thanks.
Jordan, why don't you take that one, the last bit first?
Yeah, so these are standard industry radiation-hardened transistors.
Laurie, do you want to talk about the excitement of Europa Clipper?
Yeah, so I don't think there's a worst case because honestly we're going to learn so much. It's going to be incredible no matter what we find. That's the beauty of exploring the unknown in new ways, which we're definitely doing with the incredible depth and detail we're going to get from Europa Clipper's 10 science investigations. So we're going to explore the icy shell and the ocean beneath to sensing that from our multiple flybys. We're going to be looking at the chemistry of the system. That is both the chemistry on the surface and in anything that's being emitted from the surface, any kind of plumes that will fly through and sort of taste the rainbow at Europa, and get to tell what materials are being emitted. And then lastly, we'll be looking at the surface, the geology, if you will, of this icy crust to understand the geologic history of this moon, including potentially very recent activity that would change the surface. And so we're just going to be learning a ton about the physical and chemical makeup of Europa and how it is changing and evolving over time. All of these will teach us about whether this environment is habitable.
Yeah, and I think it's interesting that the sort of the idea of the bad result. You know, as you say, there's no bad. If we go there and we find water and energy and chemistry, that opens up a whole realm of questions. If we go there and we find no water, no energy, and no chemistry, that also opens up a whole wealth of questions. Why did we think this, and why is it not there? So there really is not. This is a voyage into the unknown, and this is it's going to be incredible science, no matter which way of the equation it falls.
And I think it's important to point out that with the 10 investigations, it's extraordinarily multidisciplinary. We're sensing this moon in pretty much every way we can think of without landing on it, right? We're flying by it, but we're going to get different spectral signatures. We're going to be, penetrating the ice with radar. We're going to be looking at magnetic signatures, at particles and fields, at chemistry. Like every single way you can think of, we are going to be analyzing it. It's a very comprehensive and multidisciplinary payload, and the team will work together to sort of fuse those results into new insights for this exciting moon.
And you're hoping to do some science on the way out and at other planetary bodies?
Yeah, we fly by Mars on the way out.
Jupiter.
And yeah, that's right.
And this is Curt. If I could just add, I'll be the optimist and go back to your best case scenario. If we do get there, and Laurie mentioned the multidisciplinary approach, you need that multidisciplinary approach because answering the habitability question needs an approach from a lot of different vectors. But if we get there and we do this investigation, and the good news is it has all the ingredients and it is habitable, just think of what that means, that there are 2 places in one solar system that have all the ingredients for life that are habitable right now at the same time. Think of what that means when you extend that result to the billions and billions of other solar systems in this galaxy. Setting aside the is there life question on Europa, just the habitability question in and of itself opens up a huge new paradigm for searching for life in the galaxy.
Great point.
Wonderful, thank you. We'll move on to our next question, which is from Ken Kramer with Space Up Close.
Hi, thank you for doing this, and I'm very glad to hear that the transistors are doing great, albeit the launch. So I want to ask about the science instruments. Can you talk a little bit in detail about what they are and how they're going to look for signs of life and the plumes? Will you be flying through the plumes? Is there a mass spec to determine the chemistry there? So if you could talk some detail, I'd appreciate it. Thank you.
Well, how long do you have? Yes. Excellent. This is Laurie. Curt, is that okay if I jump in?
Yeah, definitely.
Yes, so to answer your more specific question, we do have a mass spec built by the Southwest Research Institute. So all of these sensors on board were awarded through competition. So they're built by different organizations around the country. So both the mass spectrometer and also a dust analyzer will be doing in situ kind of measurements of the actual material that's out there as we fly through it. We'll also be sensing the magnetic field, which is helpful if you want to think about a circulating saline ocean. You should see magnetic results from that. And we'll be analyzing the radiation environment there, which will be quite helpful as we try and compare to our recent test results for the transistors. Then we have a bunch of remote sensing instruments. So we're going to be looking at Europa in the ultraviolet, in the visible, with a narrow angle and a wide angle camera. The images are going to be spectacular. An infrared spectrometer and a far infrared spectrometer, which is a thermal imager, which will allow us to look for hot spots. And then we have our ice-penetrating radar. And lastly, we actually use our radio on board to sense the gravity around around Europa. So incredible science investigations, pretty much every wavelength, and in situ instruments too.
Yeah, and I just want to sort of repeat what Curt said towards the beginning, which is this is not a life detection mission.
Yeah.
You want to add anything?
Well, you mentioned what's the probability of us flying through plumes, and I will say 2 things. One, we have a couple of instruments on board that are ideally suited to analyzing the plumes. One is the ultraviolet instrument, which is a great plume hunter. It can spot the plumes from a very long distance away. And the second thing I'll say is we would love to fly through a plume, But first, we've got to be able to find them, and they've got to stay active long enough for us to get the spacecraft through them. And I think that's going to be the challenge. Now, if Europa cooperates with us and we're able to fly through one, we have some instruments on board that are going to do a heck of a lot of fantastic science with that material that we analyze.
Great, thank you so much. Our next question is from Manuel Mazzanti with Exploration Espacial.
Thank you, and congratulations on the milestone review and for sharing all this incredible data with us. Just a quick question regarding the transistors. Let me see if I understood correctly. So you didn't have to modify or upgrade them in any way, and then due to the extensive testing that you have done, you have proven that they work, and these 20 days that you have between flybys helps it to recover in a process called healing?
Yeah, this is Jordan. That is correct. So yeah, that process is technically referred to as annealing, and essentially it recovers some of the damage that it took during the radiation environment. And the way we got there is essentially we design these missions for uncertain environments, and so that uncertainty leads us to ensure that we have design margins. And so looking at those design margins and the assumptions that were made early on that just kill a problem, well, now we have to sharpen our pencils and finesse it a little bit more and get into the details of that circuit and what can that circuit take. And that allowed us to say, yes, we can do this mission with the resistors that are installed on board, or transistors, that are installed on board the spacecraft.
And can I just say, this team, they analyzed every circuit. They tested every kind of part. I mean, this was such an incredibly thorough job done by a team that has been working 24/7 since 4 months ago when we found out about this issue. And to be able to sit here today and confidently say this mission is going to be awesome and we're going to fly our baseline science is something that we're so thrilled to be able to do. But it's because of a bunch of hard work.
And Jordan, I think it might be helpful if you describe actually what you mean by what annealing means.
What annealing?
Yes.
Yeah. So it's really at the device physics level, but annealing is at different temperatures, particularly at warmer, elevated temperatures. The device itself, some of the positive and negatively charged particles that might migrate to one part under the radiation damage starts to migrate in different places, and that's a process that is fairly well known, and it's referred to as annealing. And again, it's more active as the temperature goes up. So from an annealing standpoint, warmer is better.
All right, thank you so much. Our next question is going to be from Bill Harwood with CBS News again. Welcome back, Bill.
Yeah, thank you very much. I just want to take another crack at the very question Curt was just answering. I don't understand what happens when it's in the radiation environment. If a circuit has a problem, what does that mean? Does that mean that the instrument that circuit is in doesn't work? Does it mean the data is degraded, or is it none of the above, and it somehow affects the longevity of this circuit? So I'm really unclear as to what the threat was that you were trying to resolve. And to follow up Irene Klotz's record, this is also for Curt, her question. Clearly the 39A has to be clear by some point for you guys to get off on the 10th. I'm just wondering I think she was wondering what the bingo date is for that. When does the pad have to get turned over, realizing there's some slop in that schedule? But I know you must know what that target is. That's what she was asking. That's what I'm asking. Thanks.
Bill, this is Jordan. I think you meant to direct those questions to Jordan Evans, the project manager. So regarding the transistors, every one of those circuits is different, and the consequence of the MOSFET degrading below what we could tolerate is different. In some cases, the switch just basically goes on permanently, and if that switch was turning on a little 1-watt decontamination heater, well, then that's really not a big deal to the mission. But if that circuit is telling the spacecraft that it needs to go into safe mode, that's a little bigger deal. That's a much bigger deal. And so we analyzed every one of those circuits and how robust and tolerant they are to degraded transistors. And again, determined that we had sufficient margin in every one of those circuits to accomplish this mission, flagship mission, with confidence. And then again, regarding the pad, as Dr. Fox pointed out, NASA's Launch Services Program manages that. The spacecraft itself doesn't actually go out to the pad to mate to the launch vehicle until a few days before launch. And so it's really about the time it takes to ready the pad from one launch to another, which is really a launch services program and the launch vehicle provider.
And of course, we can always follow up as we get more information. We share all that information as soon as we get it, and we'll post it. So, all right, thank you. Moving on to our next question, we have about 10-15 minutes left. If you want to get in the queue, remember to press star 1. But our next question will be with Marcia Smith from Space Policy Online.
Thanks so much for taking my question. I'm curious as to what we can expect during the 6-year journey out there. You mentioned visiting Mars. What is it going to look like at Mars? Are we going to get images back from it during the 6-year journey? What exactly can we expect between now and when it reaches Jupiter?
This is Jordan Evans. I'll take that. So yeah, Mars is actually part of our trajectory. So the trajectory that we fly to Jupiter is a Mars-Earth gravity assist. So 4 months after launch, our primary function at Mars is to steal a little angular momentum and slingshot ourselves out, and then about a little over a year later, we come back and do the same thing at Earth before heading out to Jupiter. And so because Mars is there, we have an opportunity to do some calibrations on a couple of the instruments. And so we do plan, but those are secondary to the gravity assist itself. We do plan to do calibrations of a couple of instruments when we're at Mars. We don't plan any calibrations at Earth. And so over 5.5 years, we will be doing checkouts of all of the different systems. We will be doing a simulated flyby while we're not around any particular body, and then we will certainly be preparing for our Jupiter orbit insertion in April of 2030, and then the start of our science tour.
Will we get images before JOI as we approach Jupiter? I can't remember if that's in our baseline plan.
Do you know, Curt?
We have the ability to do so. I'm not sure if we're planning on doing that, but there will be calibration activity.
Yeah.
The imaging at Mars will be very limited because the cameras, one of the cameras will still have a cover on it. You have to remember these instruments are designed to operate at Europa and at Jupiter, which is a much different environment than, say, Mars and Earth. So we have to be very careful in our use of the instruments before we get to Jupiter, make sure that we don't damage them inadvertently by trying to get data.
All right. Next up, we have Stephen Clark with Ars Technica.
Hi, thank you. I think my question is for Jordan as well. You mentioned fueling starts later this week. How much propellant are actually loading into the spacecraft? Do you have a figure for that? And can you kind of walk through some of the steps, just practical, logistical steps on the spacecraft side to get to the point where you're ready to mate up to the Falcon 9, or Falcon Heavy? Thanks.
Sure. So I'm going to speak in rough numbers on the fueling. I know first and foremost, we fill the tanks full. So there's no limitation that we only need to go partial because of mass limitations or anything like that. And so it's roughly half of the spacecraft, so roughly 3,000 kilograms of propellant and oxidizer, because we're a bipropellant system. And the second question was regarding the steps to get out to mating with the launch vehicle out to the pad. Is that correct?
Sorry, beyond.
Is he on? Okay, yeah, so with respect to that, so fueling operations takes a little over a week. We have some margin on the back end of that. And then we start what's called joint operations with the launch vehicle, and that's where we mate to the payload attach fitting inside the clean room where we are at Kennedy Space Center. They bring in the two halves of the nose cone, the fairing, and mate that up. They put us on the back of a transporter, set up our purge and air conditioning, and roll us out to a hangar that is adjacent to Pad 39A. At that hangar, we go horizontal, where we mate up to the Falcon Heavy rocket that is already in position in the hangar. We do additional checkouts there because during the ascent, our spacecraft telemetry goes through the launch vehicle, and we get the data down that way. And so we test that. We've tested early versions of that already, but we will test the final mates. And then, as I mentioned earlier, then just a couple of days before launch, we roll out to the pad and point to the sky.
All right. Thank you so much. Our next question is from Michael Greshko with Nature Magazine.
Hi. Thank you all so much for doing this. I think this might be for Jordan. Could you all just clarify kind of the timeline and how you all came to learn of the MOSFET issue specifically? And is this an issue that could potentially affect or alter the operations of ESA's JUICE mission? And if so, have you all been in touch with your partners at ESA regarding that? Thanks.
Sure. This is Jordan, responding. Regarding the timeline, so we were notified there was a conference where electronic parts engineers that deal with things like transistors meet and share, and there was an informal conversation with the chief engineer of our parts organization at JPL that said, hey, to hear about some recent data that came up from a non-NASA customer that might implicate or indicate that the transistors might fail at something less than they were originally qualified for it from a radiation dose standpoint. So I think that was 10:30 on a Thursday night. By that weekend, by the next day, we had a full inventory of all our parts. By that weekend, we stood up a Tiger team. First thing we did was get some spare parts into test, and we confirmed exactly what had been said to our parts chief engineer. And that led to 4 months of round-the-clock testing at multiple locations around the country. It led to a quest for spare parts that were the exact lot date codes and part numbers of everything on the spacecraft and instruments, and all of the circuit analyses, and led to the conclusion that we arrived at, I guess about a week ago now, that we did not find the one short straw that prevented us from the mission that we had planned to fly.
Very nice. Thank you. Mike Wall with Space.com is our next question.
Thank you for doing this. This is probably also for Jordan. Could you just say what would have been the sort of next steps if you guys did not pass this review today? Would you definitely miss this upcoming launch window? What would you have done if you gotten bad news today? Just sort of lay out what those steps would have been. Thanks.
Hi, this is Nikki. I'm going to take that one. So had they not passed today, it would have been very dependent on the reason that they had not passed the review today, whether it was we needed to delay the launch in order to do some extra work before the launch, or whether it was a very bad day and we were not able to proceed to launch. But fortunately, that did not happen, and they passed extremely well. So they'll move to fueling the end of next week. End of this week, that's right, end of this week, and then go into the regular launch flow to get the spacecraft ready. But it really would have depended on the reason that they did not pass. That would have given the severity of the impact.
Thank you so much. Our next question is from Marcia Dunn with the Associated Press.
Yes, hi. I have two quick numbers questions. Is the mission cost still projected at about $5 billion? And if you miss the October window, when is the next opportunity? Thanks.
Hey, Marcia, this is Nikki. So the life cycle cost for the mission is just under $5.2 billion. And had we not been able to continue for a launch, the next launch window would have been in 26 months. 13 months. Sorry, 13 months. I'm sorry. 13 months. I apologize. 13. Thinking of a different mission. 13 months.
There's a lot
going on right now. 13 months for the next one. Sorry, Marcia.
All right. Next up, we have Robin Andrews.
Hey there, this just a brief point on the annealing thing, just so I understand. So when the spacecraft is out of the radiation clouds, are you commanding the circuitry to warm up a bit so it can, the transistors can sort of heal their damage on an atomic level? I'm just trying to get to the specifics of what the annealing process actually is, what it's actually doing.
This is Jordan. The way you described it is exactly right. We warm them up so that they can cover some of the damage.
But even if you don't warm them up, they recover some, even at lower temperatures.
Yes.
And if you want to accelerate that, you can warm them a bit more.
Yeah, thank you, Dr. Leshin.
Yeah.
At lower temperatures, it's a lower rate of healing, and so a little extra heat helps accelerate that with each orbit.
Right.
So yeah, this is Curt. If I could just add, yeah, I want to make clear that we're only going to anneal a couple of parts right now because the rest of them are fine. Once we get to Jupiter and Europa, if we find that things are degrading worse than we expected, then we can anneal more of them. So we actually have a lot more resiliency to the European environment than we originally anticipated when we discovered the MOSFET problem. And that's one of the reasons that we feel confident launching, is that we have other steps we can take that we're currently not planning to take that are available to us in the future.
Good point.
Great, thank you. We have time for just one more question, which is Nadja Drake with Scientific American.
Hi, thank you for taking my question. I was wondering, what absorbed radiation dosage did you calculate the spacecraft could tolerate? Like, is there a number that we could put on it that could help us compare the current situation to a more ideal situation? And then expanding on Michael Greshko's question, are there any other spacecraft in operation that you're aware of that are also affected by these transistors? Thank you.
So this is Jordan. So in terms of the radiation, we looked specifically at the dose that we expect, including uncertainty, for every transistor on the spacecraft, and they're all getting different doses. Something that's outside of our shielded electronics vault, for example, will see a higher dose. And so we looked at the performance of each transistor lot date code against the expected dose with the appropriate radiation design margins that you would apply for that type of analysis, and ensured that in those circuits we still had the appropriate voltage margins coming out of the backside of them. So we did that across the board. Obviously, the environment outside of the spacecraft is extremely challenging. Millions of chest X-rays, equivalent dosage with each flyby.
100,000 per flyby.
100,000 within our reference. Yeah, but the surface, is a million. And in terms of other missions, we know that Juno is at Jupiter, and it has MOSFETs, and some MOSFETs are of a similar generation to the ones that we're flying. So that's one data point. I can't speak to other missions, but not many would have the kind of requirements that going to Jupiter requires.
All right. I think we are finished. It brings us to the top of the hour. I want to say thank you for everyone who joined us today. Thank you to our speakers and for the participants. If you did not have a chance to get your question answered, you should certainly feel free to contact me, Karen Fox, and we will see what we can do to get it answered. For more information, you can always track nasa.gov/Europa Clipper. Europa Clipper, I always wanted to say Europa, sorry about that. And thank you so much.
Thank you. This does conclude today's conference. You may disconnect at this time.